And now we will move to the second speaker. This is Mostafa from our group. Do you want to introduce? He will talk about domain generalization in computational pathology. And as you know, Mostafa and his team have won 2 challenges in the MyDoc 2021 and 2022. So can you start?
Yeah, thank you very much. That's not a humble introduction. Okay. I'll just need to share my screen. Okay. Yeah, definitely. Just need to. Right, I guess we're good. Yes. All right, thank you everyone again, and welcome to the afternoon session. I'm really glad that I also have the chance to present among these so great speakers. To be honest, I'm really proud. So today I'm going to talk about domain generalization in CPAS. So this is actually an overview of the review study that we have been doing in Tissue Image Analytics Center with collaboration of Korea University. So this really, most of the things that I want to talk about today have been already covered, so I'll be jumping through them. But before I start talking about them, I need to acknowledge the efforts that my friends and colleagues have put into this work and have actually collaborated a lot in organizing this workshop as well. There will be Manahir Reza, Robert Dewsbury, Neda Zamani, Adam, Shafet, Sean, Raza, Fayaz Minhas, Nasser Rajwood, Jean Kwak, and Trin, Bung, and Kesishu. So thank you very much. I hope I've covered everyone. So I'll just go through. Okay, good. This is the agenda to the talk today. So really quick introduction. So we know in most of the applications that we're working on today in computational pathology, automated image analysis is the core of those analysis. And with the recent advances that deep learning model had, lots of these applications are being solved by deep learning models. However, deep learning models are really data hungry. And ideally, if you want them to generalize well on scene domains, you need training data for all the domains as well, but you don't have access to that. That's when domain shift happens, and that degrades the performance. So domain generalization is come to the rescue. So hopefully we can use some techniques to elevate that problem. So what's domain shift? So as Fayaz also explained, we can define a domain first as a joint distribution over data and labels. And domain shift happens when this assumption is void. I mean, this assumption, which has been also mentioned a couple of times in morning talks, which assumes that the source and target data are independent and identically distributed. This was the assumption that have been there for a long time, and especially in machine learning. But in reality, we have domain shift, means that the joint distribution of data and label is different over source domains, the domain that you trained your model on, and the target domain, the domain that you want to test your data on. So based on the Bayesian rule, you can decompose this joint distribution into its building blocks, and based on the distribution that can happen in each of these probability distributions, we can categorize the type of domain shift. Which is the disclaimer here. This is only a theoretical way of categorizing different types of domain shifts. Or in practice, the data sets in and applications might suffer from a combination of these domain shifts, and solving them might be more complicated. However, We can classify domain shifts into covariate shift. So this happens when the distribution of input or feature space in source and target domains are different. So this is the most common domain shift in computational pathology and all other medical image analysis problems. And this can happen based on the scanner device, and the variation of the color palette that they generate, the staining variation or the slide preparation in the lab, different tissue types and different species. We also have prior shift when the source and target output probability distribution are different. This is the distribution of the labels being different in different domains. So this can also happen lots of time in computational pathology when distribution of positive samples in a binary classification is different between the domains, or different number of events in train and tests samples in a survival analysis exist. So, or a distribution shift that is almost all the time overlooked. We always train our CNNs, our deep learning models, on small tiles, but then we tried them on whole slide images, which might have completely different distribution of labels in them. The next is posterior shift or concept shift, which is basically related to subjectivity of labeling. So the process of generating labels, giving the same data is different. It's always there with the subjective annotations, such as mitosis annotation, Gleason grading, or tumor grading. And finally, class conditional shift, where the process of generating data given the same label is different. So, for example, distribution of two morphological features of the same cell label, same cell type, is different when they are measured in two different domains. And domains here will be like early stage cancer and late stage cancer. For example, a connective cell always looks the same in cancer, either it's in early or late stage cancer, but epithelial, tumoral epithelial cells, they are different in these stages. That's a class conditional shift. So domain generalization wants to solve these problems. Well, we want to include some domain generalization methods to improve our models to be robust against domain shift. So the goal is to find a predictive model from data space to label space that has almost the same performance accuracy on the target domain, but have only seen the source domain data, and there is a shift between source and target domain. But before I jump into the a review of domain generalization methods, I need to clarify domain generalization differences with the related concepts. So the first one, and the most obvious one, would be domain adaptation. So in domain adaptation, the difference is we have access to some or a lot of data from the target domain as well. Or people have been referring to transfer learning. So transfer learning usually when we pre-train a model on a huge data set or a domain that contains lots of data in it, and then use the pre-trained model to fine-tune it on own domain. So there are some other concepts which I won't go through here because of the time. So I'm jumping to this area of domain generalization. So the first, what we've done, in the review paper that we're working on, we categorized the methodology that the other researchers used in main methodological categories, which Fayaz has already introduced. I'll review them really quick. So the first category of methods is domain alignment, and it can happen in various spaces. You can align data, you can align the feature space, or you can align the classifier space. So aligning the data would be, say, the stain normalization that we've been usually used in computational pathology for many years now, or aligning feature spaces when you use, say, domain adversarial learning or gradient reversal layers in your network. This tangled representation learning does domain alignment, but something else as well. It tries to separate the feature space into domain agnostic and domain relevant feature spaces. And what it tries to do is to make the domain agnostic feature spaces similar to each other for the data that's coming from different domain. So we have domain augmentation techniques. This is obviously, we have talked a lot about this. So it includes a variety of methods for domain augmentation, like image translation, scene augmentation that we talked about a lot today, or GAN. Especially generative networks or GANs have been used exhaustively in computational pathology because they have the capability of transforming image into the domains that are really different. So, for example, Fayyaz mentioned that you cannot, if you have HN images, you should not expect the model to work on IX images. But there have been several studies that actually leverage GANs to make IX images and like augment their data sets so they can work on IX images as well. Ensemble learning is also proven to be a really effective method for domain generalization when you train multiple models on multiple domains and just aggregate the results. Self and unsupervised learning have been investigated several times in computational pathology because there are a lot of unlabeled data in computational pathology available, TCGA, CP tag datasets. You can leverage those datasets to pre-train your network to extract relevant feature space. So you can use in subsequent analysis. So you can use those features instead of ImageNet features in MIL studies, in forming graphs for whole slide images. Various methods have been proposed for self and unsupervised learning. One is self-pass, which is trying to solve several pretext tasks for computational pathology. We had in-pash model that Jintai mentioned today. We also have model design. Papers that investigated a specific model design for their problem, which can be very, very effective for certain problems. Among them, multitask learning can also be categorized in this category because with multitask learning, you design models capable of solving different tasks together, and has been shown in several studies that these models not only they generalize well to unseen domains, but because they are able to solve different tasks and different problems together, they can be really effective at handling computational pathology when we are dealing with big whole slide images. Regularization studies have been investigated several times, methods such as dropout or more sophisticated version of them. And meta-learning also is a method that gaining more and more attention. So this is basically a technique in training your network, not a real specific method. And what it does is it's really flexible. It allows you to include more techniques such as contrastive learning, domain adversarial learning, or domain augmentation, all kinds of techniques. You can use it in conjunction with meta-learning, which makes it really nice framework. So, so based on the review that we've done on almost all the papers that we could have found that have incorporated domain generalization in their CPAS study, we could have formed these plots. So this shows you what method have been used to deal with what kind of domain shifts and what kind of application. So as you can see here, and as we expect, covariate shift is the one that has been mostly addressed in the literature, but prior shift and posterior shift, although they are very important type of domain shift in computational pathology, they have attracted less attention and that needs to be addressed really. We think that the main reason for that is that, so one reason that covariate shift or other studies have focused on covariate shift, we think that because of the availability of the data and the challenges that have been, challenge contests that have been organized to deal with that, but we don't have much specific data sets or challenges that address two or the last one, class conditional shift as well. So if we have those kind of challenges and data sets available, that can help that issue. And also on the right-hand side, you can see the distribution of different applications. You can see most of the applications that have attracted attention for domain generalization techniques is classification applications. But as you can see, survival applications, they often do not investigate or include any kind of domain generalization study or domain generalization techniques in them. So because it's really important, that might be the most important kind of study that we do in computational pathology that requires more attention. So how much time do I have? 5 minutes ago, I'll be quick. So as a part of the paper, we also put it together a list of resources that you can use for domain generalization study. But if you want to find the best domain generalization method for yourself, or you want to investigate domain generalization as a research line in computational pathology, you can use those. So we've categorized the resources into data set and toolboxes, and we put together a good list of. Actually, Manal has worked on this mostly, and she put together a comprehensive list of data sets and toolboxes that you can use, which I'll quickly go through. Yeah, as you can see, these are like really generic insights on them. So what would be a good survey without a benchmarking experiment? So we also try to, so actually this is the reason behind it. While we were reviewing the methodologies, different methods for domain generalization, we found out there are many methods for domain generalization out there proposed for in generic ML society or computer vision community that has not been investigated in medical image analysis or computational pathology. So we decided to try it. I'm leveraging one of those toolboxes that we reviewed, domain bed. We've tried several different domain generalization methods on mitosis versus mimicker classification application. So we use MyDoc22 dataset. This is a good data set because the attributes that this data set has, it contains several types of domain shifts. So it has query shift because data set is coming from different centers with different scanners. It has priority shift because the number of mitotic cells and mimickers labeled in different domains is different. The distribution of the labels, sorry. And also there is posterior shift because mitosis labeling is subjective task. So we used a ResNet-15 model and investigated 27 different domain generalization methods and HSV stain augmentation as a domain specific or modality specific data augmentation technique as well, or domain generalization technique. So interestingly, we found that using simply stain augmentation, you can outperform all other fancy domain generalization techniques for this particular task though. We cannot say it's always the case, but we found that with different tasks, you need to try different methods to see which one worked for you the best. We also found that even using ERM, which is like basically using the data you have and just in a good training setup, you train your model, you can get better results than lots of other domain generalization techniques. Yeah. So based on the reviews that we have done, we've put together some guidelines to domain generalization. These guidelines can be useful for people who want to include domain generalization in their application and their CPAT study, or they want to pursue domain generalization studies and come up with new methods. So the first step is to identify the type of domain shift. So we give some guidelines on how you can identify what type of domain shift you have. We also put some references and guide people toward the related studies that they can find out that. And based on the type of domain shift that you detect in the data set, based on the type of data set you have, and based on the application you're solving or the problem you're working on, you come up with some simple guidelines to handle your domain shift. So it's not a causal view on proposing a solution with domain generalization. As I said, it's based on the problem and the data set you have. So depending on, so if you, for example, if you're working with covariate shift, if your problem is covariate shift, depending on if you have data from single source during the training, or you have data from multiple source domains, you will have different options to fight with domain shift. Oh, that's all right. I'm just done. So yeah, we will put the preprint of the paper on archive very soon. So you can follow me on LinkedIn. I'll just put the word out, and we will have a really detailed explanation and discussions about all the stuff that I've just told you today. Once again, thank you very much for coming in today, and thank you all my teammates and my colleagues to putting this work together. You good?
If anyone has any questions. feel free to ask. Otherwise, we're gonna move to the next section with the case study and brainstorming. I guess we should have more.
Good question. So in your comparative analysis, you compare the different domains and validation methods.
Yes.
Did you try anything that does that extreme kind of filthy augmentation that was talked about this morning?
Not really. So with all the methods here, it's apart from standard augmentation, which is standard data augmentation techniques like translation, rotation, scaling, these kind of augmentations have been used, except for stain augmentation that we also use color augmentation, which is some sort of a causal augmentation to the problem that have. Yeah. So not really extreme augmentations, but they ought to work better if you add those. So this augmentation can be really effective. This is actually what we found in another work that I've done in mitosis detection. I didn't investigate this much, but I investigated like 5 different domain generalization methods for mitosis segmentation, and stain augmentation worked better than all of them. Yeah. All right. Thank you very much. So I guess with that, I set the space for for the case study. So what time is it? So we had around 15 minutes to do this. That's really nice. Can you guys distribute this? All right, yeah. So we've decided today to better use the atmosphere here and the knowledge that we gained today. We decided to come up with a case study and have a brainstorming in groups on a typical task in computational pathology, which includes domain shift and domain generalization, and see if you can come up with good solutions to the problem. So what we will do, go on.
There's one person online. What do you want them to do?
Yes.
Oh, he's gone.
He's gone. All right.
All right.
Okay. So what we do is to ask you. So how many people are here? 1, 2, 3, 4, 5, 6, 7, 8, 9. 25 people. So I guess we can group into group of 5 people. So I'll need you guys to group together. So, and I want to ask the professors and faculty members and our guests here to be in one of the groups. So each group should have one of you guys in them. No, that's not fair. Yeah. So what we do, so my friends here are handing over a paper to you, which has explained the case study to you guys. So basically, the problem that we are going to solve today is mitosis detection. Again, lots of mitosis. You see, this is effective data set in domain generalization problems, because Mark Overville and his colleagues put together these good data sets out there. It has boosted domain generalization in computational pathology a lot. So we are going to solve the same problem. So this is mitosis detection in histology. And so for those who don't know that, so mitosis is a special kind of cells, as you can see here, you know, mitosis, right? But it's really challenging to detect these cells because, first of all, they're really similar to non-mitotic cells. They might find in histology images as well. And there are some other issues with this problem, like domain shift, as you get various kind of appearances of images coming from different scanners, right? And there are some intrinsic problem with mitosis detection. For example, the mitotic cells are rare events in whole slide images. And there's always intra and interdissimilarity of mitotic cells. And as I said, it's a really subjective task. So, go on.
Do you want to continue with the Zoom recording?
Yeah, we can stop it. Yeah.